Mr. White.
And Mr. Sadler.
And today we're going to develop equations for projectile motion.
So you're going to do the work that you need for the chapter challenge, basically.
Yeah, we're gonna get them started. And the first thing, we're going to talk about two specific cases. We're going to talk about a launch angle of 0 degrees, which we spent a lot of time observing and saying gravity acts the same whether we drop an object straight down or whether it's kicked off the table sideways. Okay, the delta t is the same. Okay, but we're going to really break that down today. And then we're going to go with theta not 0 degrees.
So I'm launching something up or down? Or
Launching something up. We're not going to do the launching down. We'll save that for college.
All right.
Okay. So the theta is 0 case. So if we've got a table or a cliff or whatever, okay, and we kick a ball or flick a penny, it's going to take this general half parabola path, right?
Mm-hmm.
To do that, I gave it some
initial horizontal speed.
Right. Now I'm going to call it VI, but the fact is, if the launch angle is 0, all of the velocity is in the x direction. Is that true?
Correct.
So we're going to say VI, it's VXI.
All right.
Okay? We know that at each moment in time, it's going to fall along this path.
Right.
Okay? We know that.
But in the x direction, we don't care about that initially, right? We're just seeing where it's going in the x.
Right. So I'm going to continue with my red theme here. It will go some horizontal distance x because it had some initial velocity.
Correct.
So if I were to develop some equations for that, I would say, well, in the x direction, that would be dependent on the x velocity, the speed with which it leaves the table,
times the time.
times the time. I'm going to put that in black.
Okay.
Okay? Does that make sense?
Absolutely. And I know that it's going at a constant speed in that direction.
VI is VXI. They're the same thing. Okay? There's no other variables to associate because horizontally speaking, is there a force speeding it up or slowing it down? So then we know that the horizontal acceleration is 0 meters per second squared.
Right.
These are your x equations. Really, there's one equation, right?
Right. And x is pretty easy, right? Because
X
I've
isn't
got
terrible.
constant motion, where in the y I've got something else going on.
That's correct. Now, the vertical is a little messier because of
gravity.
Gravity. Now, I'm going to start in the reverse order. I'm going to say, hey, the acceleration in the y direction is due to gravity, or this negative 9.81 meters per second squared. That's a number we know. It's constant, set in stone.
And generally we want to show gravity as negative, right?
That is correct. Because it's acting downward.
Correct.
Okay. The initial vertical velocity, according to my diagram, is what?
0.
0. Because it's not moving up or down to start.
Initially, right.
Right. The final vertical velocity would be equal then to its acceleration due to gravity times the time. This is just a variation of an equation we saw in Chapter 1, where the final velocity was equal to the initial velocity plus acceleration times time. Well, initial velocity is 0. Gravity is our acceleration. Now notice I put the scalar term that connects everything in black.
Right.
Okay, we need to know time to do anything. That's often difficult to find.
Well, and I can't find the object if the time isn't the same in the x and the y.
That's correct.
Right.
So it's the thing that links it together so that we can give each one of these dots an x and a y position. The good news is I usually have the ability to find the vertical displacement. And so delta y, once again, comes from an equation that we already saw. Last chapter, it was delta x is vi delta t plus half a t squared. Well, vi in the y direction is nothing, so that term goes away. Half of gravity, I can find that. If I know the vertical displacement, and I know half of gravity, guess what I can find?
The distance.
The time.
Oh, I'm
Right?
sorry,
I can find the time, and then I can go back and find the final y velocity, which is how fast is it going down as it crashes, and I can find the final x displacement. And so if I can't, I've got to find a way to find time to link all of this stuff together. This is the fundamentals. These are the basics. Okay? So if you know the height of the ledge, you know the initial launch speed, you can find anything.
Correct.
Okay. That's a special case. That's the zero case.
So that's if I'm launching something horizontally.
That is correct. Every other case is different. Every other case assumes a non-zero launch angle
I'm launching it into the air with some velocity.
with some initial velocity. And so I'm going to keep my color scheme the same. Okay? What do we see here? Well, this does have some initial x velocity. And from the last podcast, we know that that's equal to VI cos of theta. If you know the launch angle and you know the launch speed, you can tell me how fast it's moving to the right.
Correct.
You can also tell me how far it's gone horizontally. And so we did this a little bit on the last couple slides. Well, the change in position is equal to the x velocity times the time. Right?
Right.
Well, the x position is VI cos of theta times the time. Instead of VXI, which maybe is given, but I doubt it, you can substitute in, because you know the hypotenuse and you know the cos of the angle. That's just a number. This is how you find the horizontal displacement. Okay, so that was one thing that we worked on the last slide. Next thing, okay, is Vx always, okay, the horizontal velocity is always equal to the initial x velocity, or specifically VI cos theta.
Right.
And just like in the 0 degree launch angle thing, is there a horizontal acceleration?
No.
No, it's just...
Going the same speed in the horizontal.
So yes, our equations got a little more complicated because of some trig, but no, this is not impossible. Okay. Now,
So that's X. So now
that's
we're going to
X.
look at Y.
Now we got to look at Y. Y, once again, because of gravity, is a little trickier.
And we're going to go up, and then it's going to, at some point, it's going to be 0 and come back down.
Right. So there's a lot going on here. This is Vyi, which of course is going to change because of gravity. Remember, Vxi is constant because there's no horizontal force. But this, the initial, is going to be Vi sine theta because it's the opposite side of my triangle. I know the hypotenuse. Theoretically, I know theta. Okay? That's important. Once again, I'm going to start with Ay because it's gravity and it's constant. Done.
Right.
The final vertical speed would be equal to the initial vertical speed plus g delta t. We're just varying the equation we already know, substituting in more specific things. Well, I know Vyi, don't I? I've got a very specific answer for that. It's what?
It's Vi sine theta.
So Vyf is Vi sine theta plus g delta t. Now I've messed up and need to put my t's in black. There we go. So I've got this nice thing for gravity and I've got this nice thing for speed. Now delta y is tricky. Okay? Just for the sake of argument, would you say that this is a parabola, Mr. Sedler?
Yes.
Yes. Is it uniform in its shape?
Is it uniform in its shape? Yes.
Yeah, it is. There's nothing mysterious about parabolas. Now, I've messed up my picture a little bit here. Let's go with a new color. That point right there, we would define as the peak, right?
Yeah, the peak.
It's not moving up or down
Right.
at that point. You know all kinds of things about this point. You know that the vertical velocity right here is 0.
Right.
You know that gravity is still acting on it.
Right.
And does this appear to be halfway through the flight?
Absolutely.
So,
So if they give me the time, I know I can find where it's 0.
right. So, yes, I need to know about the initial y velocity that got me there. Okay. And that's only half the time. So there are ways to work through this. That's one way. One way is to analyze the peak. Okay, I cannot make that clear enough. Now, you also have an equation, by the way. What if you were to call this the beginning and this the end? We have an equation from before that doesn't have time in it. We would say VYF squared, which, by the way, is 0, because I'm calling this my end, just for the sake of argument, is equal to this whole initial term, square that mess, plus 2g delta y. So, delta y is how high it went. And then you can work backwards, and you can tell me how long it took to get there. You can double the time and tell me how long it takes to get to the end. This is one solution. I'm not going to say it's the easiest one, but if it makes sense to you, I recommend that you use this one.
So I'm really breaking the motion into 2 motions, the up and the down.
And the down. And we take advantage that we know that it's not moving up or down at that point. It is still moving to the right. But remember, we're only analyzing the up-down because we're analyzing vectors.
Right.
The other way. The other way is to say, hey, look at this. Bear with me. That's a parabola. Okay. You know what? Let's just start that over. The other way is this. It starts here, right?
Right.
It finishes here, right?
Mm-hmm.
What is its total vertical change?
0. Right.
0.
Its displacement is 0.
Don't worry about what happened in the middle. This is where it started. This is where it ended. Right?
Right.
Okay. And so you know that, yes, this equation is valid. Okay. But if you know that this is 0, you have power. You can use some Algebra 2 analyzing the quadratic formula to work your way through. If you know the launch speed and the launch angle, and since gravity is a constant, well, then you've got to do some work and you've got to determine the time of the total flight. This is another way to do this question.
And then if I find the time, I should be able to find the distance.
The range, right?
Right.
The horizontal distance, or we call it the range. There's a lot of ways to analyze these problems. But when it's time to do shoot the grade, we're going to give you VI and we're going to give you theta. You know that your rings are going to have to be lined up in some sort of parabolic shape. What you're going to find for each one of these, maybe I should do this, is an X and a Y to place that ring. Okay? That's what you're going to find every time. This is Y1, that's Y2, that's X1, this is X2 for the second ring, etc., etc., etc. You have the ability to do that because we just showed you how to find delta X and Vx, and we know that this is 0. And we just showed you how to find delta Y and Vy, and we know that this is 0, or we know that this is negative 9.81 meters per second squared.
Correct.
So that was the dismissal bell that you heard in the background, so we have to sign off now. So this is Mr. White.
And Mr. Sadler.